in 3 different perspectives. So, one is scalability in terms of transactions per second. So you'll often hear people say, well, Bitcoin has 7 transactions per second, or Ethereum has 10 or 20 transactions per second, and this new protocol has 200 transactions or 300 transactions per second. There's this notion of how many transactions am I able to get into a block within some finite period of time. But it's not the only thing that you have to concern yourself with. Transactions carry data. And as you get more transactions, you require more network resources. So there's also this notion of bandwidth or network, where for a system to scale, if it's going to go to millions and billions of users, that system could require hundreds of megabytes to gigabytes per second of bandwidth to be able to support all the data flowing through it. This is very common in the enterprise world, but not quite where we need to be in the peer-to-peer world. And then finally, there's this notion of data scale. So blockchains store things, hopefully, forever. And so every time you put a transaction in, regardless if it's relevant or not, it ends up in the log. And as you have more and more transactions per second, you need more and more data. And as a consequence, blockchains will grow from megabytes to gigabytes to terabytes to petabytes and potentially even exabytes. Again, this is okay in the network world, but when we talk about a replicated system whose security model relies upon each node having a copy of the blockchain, this is not tractable for consumer hardware devices. So, Cardano, what we're trying to do is figure out ways to solve these problems in a very elegant way. Namely that as we add people to the network, we naturally get more transactions per second, we get more network resources, and eventually we'll get more available overall data storage without compromising our security model. So let's talk a little bit about some of the innovations we've already brought, namely with the throughput. We've developed a peer-reviewed white paper for a provably secure proof-of-stake protocol. Called Ouroboros. And Ouroboros is among one of the most efficient consensus protocols in the cryptocurrency space. And it's the first to actually be proven secure in a very rigorous cryptographic way. The magic of Ouroboros is that it's been designed in a modular way. And it's been designed with future-proofing in its DNA. So, namely, how Ouroboros works is Ouroboros breaks the world into epochs. It takes a look at the distribution of tokens, and from a source of random numbers, it's able to hold an election and create slot leaders. Now, these slot leaders functionally do the exact same thing that a miner would do in Bitcoin. So this is basically the same as a person who discovers a block, wins a block in Bitcoin. But the difference is that it doesn't require the extensive computational resources that Bitcoin requires to construct a block. And as a consequence, this system is considerably cheaper to run, even though we still have similar security guarantees that Bitcoin currently enjoys. So it's a major advancement. But the other really interesting thing is that these slot leaders don't have to just maintain a single block and a single chain. They can actually maintain other blocks and other chains. Because the cost of constructing a block is so low, it's actually now tractable to talk about consensus over a range of blockchains instead of a single chain. Furthermore, epochs perhaps could even be run in parallel. So instead of having one epoch run and then another epoch run, one could develop a system using Ouroboros where epochs run in parallel and transactions are partitioned accordingly. What this effectively means is as you gain more users and your users gain more capabilities, these slot leaders will be able to maintain more types of blockchains and also run transaction processing for blockchains in parallel. This is a major advancement. The other cool thing is that Ouroboros has very rigorous security standards in terms of its theoretical foundations as well as its implementation. So as a consequence, as we develop new capabilities for the protocol, these capabilities are somewhat composable, meaning that these capabilities will also be secure. Whereas other systems, one has to prove these things on a case-in-case basis, in some cases make major modifications or changes to their system. In addition to this, we intend on Ouroboros actually being quantum resistant sometime in 2018, hopefully, where when the slot leader signs these blocks, they'll be using a quantum resistant signature scheme, so we can get even more future proofing into the system. So that's kind of the first view, is how do we construct a way of maintaining the network that doesn't cost $300,000 an hour, which is what Bitcoin currently costs at the current market rate of $5,000 per coin. And how do we build a system that allows us to go parallel and also allows us to potentially maintain multiple chains concurrently? This is the heart of Ouroboros. Now, as we mentioned before, one of the most important things when one develops new cryptography is to make sure that this cryptography is developed in a very rigorous, peer-reviewed way. So Ouroboros actually was accepted at Crypto 17, where our team went there to present it. And future versions of the protocol continue to go through more rigorous peer review, giving us a high assurance that the conceptual design of the system is correct. The other side of it is we're actually modeling a formal specification of Ouroboros using Psi calculus, which is a wonderful formal modeling language that's machine understandable, that eventually we're going to be able to connect to the Haskell code in our GitHub repo and actually show that we've correctly implemented the protocol. This is a standard that actually does not exist in our space, and we're very excited to be the first to bring it to the space. But that's not the only thing required for scalability. You also need the ability to move large amounts of data at the same time. As our network grows from a few hundred transactions per second to thousands, to tens of thousands, to hundreds of thousands of transactions per second, you cannot maintain a homogeneous network topology. In other words, you cannot have a situation where every node has to relay every message, because there will be nodes that don't have those capabilities, especially as they grow. So we're actually looking at a new type of technology called RENA. And this stands for Recursive Internetwork Architecture. And so RENA is basically a new type of structuring networks using policies and clever engineering principles, mostly conceived by John Day, who's based out of Boston University. And the goal here is to build a heterogeneous network that gives you similar types of privacy guarantees, transparency guarantees, scalability guarantees that you would expect to get from network protocols like TCP/IP, but do so in a way where you can actually reason about how the network is going to compose in a formal capacity. So in other words, RENA is a major step forward that will give us a way to very naturally tune and configure Cardano as it grows from hundreds to thousands to tens of thousands of transactions per second, and something that will very seamlessly connect and interoperate with TCP/IP. We're very excited to bring this in part to the Cardano ecosystem in 2018 and completely around 2019. And we think it will be a big solution to a lot of the network overhead issues that we have. Finally, we have this notion of data scaling. So this is among the hardest of the problems, and it's one that we're still examining and looking at. But the reality is that not everybody requires all the data. The transactions that Alice sends to Bob are not necessarily relevant to Eve and Jane and Bill. They're only relevant from the context that these people are able to infer from them the total ownership of the money and know that the tokens they've received are legitimate and correct. So you have techniques like pruning. You have techniques like subscriptions and some form of compression, which when applied in a setting in a very intelligent way can actually reduce substantially the amount of overall data one user has to have. There's also the idea of partitioning. Partitioning is where a user doesn't actually have a full copy of the blockchain. Rather, they have some chunk of the chain, as opposed to many other chunks. And there's some notion that you can put all of these things together. So one of the goals of the Cardano project is to study this in a very rigorous way and to come up with new blockchain architectures as they become necessary that will allow people to have much smaller amounts of data, but overall still get the same level of assurance and security that the transactions they receive, the computations that are performed, are correct. So part of this research also involves some of our ideas about sidechains. And we'll get to that actually when we get to the interoperability section, but as a brief mention, all a sidechain really is two components. First, it's the notion of creating a compressed representation of a blockchain, and it's a notion of creating interoperability between chains, i.e. a way of translating transactions between chains. So some of the proofs that we've come up with some of our recent sidechains research give us a lot of hope that we can create compressed representations of a blockchain as it grows from gigabytes to terabytes to petabytes, and that these proofs can give us a high level of certainty that the transactions we're seeing, the history we're seeing is correct, even though these proofs are quite small, megabytes to kilobytes. So this is kind of our solution to data, is to approach it in both a pragmatic way, where we start restricting, in some cases, what people see in a very intelligent case-by-case basis. We partition things where and when we can, and we find out really intelligent cryptographic ways to compress history, which give us the same level of confidence even though we don't have all of it, but do all of this in a way where we don't remove the original replicated security guarantee that Bitcoin has endowed the space with. The other fortunate thing is, well, TPS tends to grow quite a bit, and network resources also tend to grow quite a bit. Storage is still relatively cheap and available, so we believe that the data scaling side of Cardano will be something that we don't have an urgency to resolve until late 2018 to mid-2019. The research has just started at the University of Edinburgh, and we intend to continue it, and we believe we'll have our first approaches probably by the middle part of 2018, and eventually have a total solution to this problem by the end of 2019 for the system. So this is kind of the first component. Let's build a protocol that allows us to scale up the transactions per second. So as we gain more people into the ecosystem, we get more throughput. Let's create a network stack developed by one of the early internet pioneers that has learned from some of the issues that TCP/IP has in other systems, and is a bit less fragile and a bit easier to configure and tune so that it can handle a large heterogeneous network based upon real-life scenarios. And let's come up with some clever ways of handling the use of data in our system without compromising our security guarantees. And also, when partitioning is adopted, so much like BitTorrent, you actually gain a lot more resources for overall storage. So if we don't have to replicate the database, rather we can distribute it, there is some hope that we can build a large distributed file system for Cardano, and thus actually have total available petabytes of data, even though any particular user only has to have a small amount. So that's the first pillar, this notion of scalability. But the third generation demands two more, and therefore for the Cardano project we will do these things. First, there's this idea of interoperability. So interoperability is this idea that there will not be one token to rule them all. So sorry, Bitcoin. You're going to have many networks like Ethereum,